welcome everyone. So this is going to be geospatial visualizations using R. 3-hour whirlwind tour of everything that R has to offer for geospatial visualizations. My name, as you can see, is Bhaskar Karambelkar. And yeah, PN Vinevu, welcome and welcome. So this tutorial is all about choices, right? All the choices that you have for geospatial visualizations using R. And unlike the US political system where you have to choose the lesser of the two evils, this thing, you have a lot of choices. So there is really no chance of getting you wrong like we got in the US political system, right? Then I'd like to introduce myself, and then afterwards I'd like to get to know you guys a little bit more so that I have a better understanding of the audience that I'm talking to. Finally, defining the scope of the tutorial. For those of you who have already seen, nothing new here, but for those of you who have just walked in without knowing anything about it, the setup that is required if you want to follow along. Again, as I said, this is a completely flexible tutorial. You are perfectly fine just to sit through this and watch all the slides go by. If you want to play along, just fire up your RStudio, and I hope you have set up all the stuff that I had mentioned in the email that got sent out to you, or in one of the Twitters if you were following on the Twitter feed. And then we go on to part 2. So there are 7 total parts for these tutorials. They're not too long, but they are quite extensive. And that just speaks to the nature of how much choice you have in R when it comes to visualization, right? And the way I have built this tutorial up is, it's a stacking block of things. So you start with the basics of the R packages that you have available, and then you keep on going until you have started building maps for your needs. So myself, my day job is absolutely nothing to do with GIS related, but it's a hobby that I take really very seriously. And I actually work in information security, and if you ever meet people who work in information security, don't ever tell them that you know anything about cybersecurity. We hate the word cyber, okay? It's just, don't ever cyber anybody who works in information security. I absolutely love maps, and I absolutely love R. I've been using R for almost 5 years now. So there's a good understanding of R as far as I'm concerned. The reason I got into GIS map, especially with geospatial visualization, was because I had a boss called Bob Rudis. Anybody know him? He's pretty active in R development as well. He has a lot of packages put out. He was my boss, and he sort of got me into it. My original requirement was really simple. About 2 years ago, I was working on an information security project that was going to be published, and we had to put certain information on a map. And at that time, somebody who was already working on that project had taken screenshots out of Google Maps, and it was literally horrible, these low-resolution JPEGs with everything. And I thought, we can do better than that, right? So I just started looking at the options. Since I already knew R, I was looking at what R had to offer, found out about the leaflet package and started using it. And one thing led to another, and I started contributing some code back to the leaflet package. And Joe Chang, most of you guys must know him. He's the CTO of RStudio, and he's one of the original authors of Leaflet, which is a package. If you don't know about it, we'll talk about it. So he was the original author of that, and I gave him some pull request on GitHub. And I had completely expected him to blow me off. Who the hell are you? You don't know anything about any of this. Why are you giving me pull requests? But surprisingly, Joe being this awesome guy, he was oh, this looks awesome. Do you want to start committing to this? And so that's how my journey into R started. What? Okay. So, so far I've contributed some code to the leaflet package. I've worked on it for last almost 2 years now. And then I also have some extra packages of my own called leaflet extras, leaflet E3, tilegrams, widget frames. If you have used some of those, good. If not, you'll find out a little bit more. And now I would like to know a little bit more about you guys. So how many of you are like completely new to R and GIS both? Like, just completely new to both these? Okay, somebody. How many of you are completely new to R or like maybe novice to R, but like GIS professionals? Like you have ArcGIS experience and stuff like that. Okay, good. So you guys will hopefully get quite a lot out of this when it comes to like using R as opposed to some of the proprietary tools. How many of you are like experienced with R but new to like GIS or visualizations? Oh, awesome. So you are like, I was hoping that you would be my target audience because I don't have to explain a whole lot of R code to you guys, but I can always talk about the GIS packages and options available. So that's totally awesome. And how many of you are like experts in both GIS and R, or consider themselves as expert in GIS and R? Okay, get out. Just kidding. No, I mean, I still hope that you still get something out of it. As I said, it's quite an extensive tutorial, so maybe you'll find something that you haven't come across before. So for people with programming experience, overall, like every programming language starts with a hello world, so I thought, why not start a map application with a hello world, right? Like that's kind of neat over there. So that's a hello world in R for maps. It's just a simple map of the world, and as you can see immediately, even if people who have no experience in coding, I'm saying that, fill all the polygons, give that a certain color, the border should be black, and the background should be, whatever that you see over there. That's just it. I don't know if you can see. The contrast is not really good over here so that you can see the background image, but trust me, like if there is a background image there. Like there is a background color over there. So, for those of you who have not seen this, I will conclude probably the first part by 9:50, maybe a little bit earlier. It's about 9:40 now, 9:35. Oh, so, okay, that's good. The second part will be R packages, where I'll discuss all the R packages that are available for you for spatial data visualization. The third part then starts with the representation of spatial data in an R session, right? Like what are the data structures that you have for spatial data? Then you start with like how do you operate on those data structures? What sort of operations you can do on that? By the way, I did tweet out yesterday that the slides were uploaded. Anybody had a chance to take a look at the slides? Yes, yesterday night? Okay, good. So you're seeing it for the first time. That's nice. So after spatial data operations, we are going to come to a very important part, which is like, how do you output these maps, right? You have plenty of choices when you come to presenting these maps. And the reason you would want to do that is simply if you're doing spatial data exploratory analysis, it's just mostly just looking at them in RStudio. But then if you are working on actual projects and reports or books or whatnot, then you want your plots to be much more sophisticated, much more production ready. So what are the options available for you when it comes to outputting maps? And people who are like into data-driven journalism, who are into like report writing, paper writing, they'll get hopefully quite a lot out of this. I've put some effort into that part. And then we'll break at around 11 o'clock for 30 minutes. So the core of mapping still doesn't start till we get to part 5, right? Like because we need to build up on that stack before we can start building maps in R. And since a lot of you are new to mapping, I think you'll find that pace just fine. And the last 2 sessions that we'll have after the break will be about making static maps and making interactive maps. So this will essentially be the hardcore core of all the map making that you'll see. So how many of you guys are from technical background, know Docker? By the way, I'm going to ask you to raise your hands once or twice. Please don't feel shy, and if it hurts your arm, bear with me for a moment. How many of you know Docker well? Okay, quite some of you. I really wanted to make this tutorial as easy to set up and as painless to set up as possible because it was like a 7-part tutorial. There are quite a lot of packages that we are going to go through. So the best thing that I could think of was make a Docker image out of it. For those of you who don't know what Docker is, it's essentially a way for somebody to give you a pre-packaged application, if you will, that you can easily run in any operating system, regardless of which operating system you are running. So you could be running Linux, you could be running R, you could be running OS X, you could be running Windows. As long as you have the Docker software installed on your box, you can pull in the Docker image and start running with it. Right? That's the gist of it. And that sort of, what happens is you don't need to do any setup, you don't need to install any packages manually. Everything is there for you. So even if you haven't set up Docker now or you don't know about it, like whenever you find free time or maybe after the tutorial, just go read up on Docker. It's fairly straightforward to get started, especially just using Docker. Install it, you can start pulling in the Docker images and start running. So there is already a repository called Rocker, which was built by some of the R folks, which gives you Docker images of a lot of R-based tools, right? There's one Docker image called Tidyverse, which is basically all, Hadley becomes Tidyverse, everything ready for you to test. There's another called, I think, Shiny, which has like the Shiny server built in. So even if you don't have anything about Shiny, you can still take that Docker image, run with it. The one that I based my Docker image on was called R Geospatial, and that had pretty much a lot of geospatial packages installed to get you started, but not a whole lot of packages when it came to like data visualization. So I built on top of it, and I just like call it Bhaskar VK RGeo Data Viz. And if you were to run this command, please don't run it now if you are trying to do that, because that's like a 1.6 GB image. And I'm pretty sure you'll crash the Wi-Fi if all of you start doing that now. So yeah, do it offline if you haven't done that. But the good thing is, once that 1.6 GB image is completed, if I make further contributions to this Docker image, like maybe I put newer packages or updated versions of certain packages, then next time you do a pull, it's only the delta, right? It's only the newer additions that go into it. So the first pull takes a lot of time. The subsequent pulls, as the image gets updated, is very fast. And then once you have pulled that image, you need to run it, right? So a fairly straightforward command, even if you don't really know command line, as long as you know how to open a command line application in your programming language choice, in your operating system choice, you should be fine, right? Like this is just a command that says Docker, run this image. I'm giving it a name called RGeoDataViz, and I'm opening a port called 8787 on it. That's the port where RStudio runs. And if I can actually show you what happens. So once you have that running, you will have, yeah, that's just because of all the mismatch in the resolution. But once you have it, you can go to localhost 8787. It will ask you for a username, password. You can enter RStudio, and then you get to this. One second, let me probably restart Chrome. I think that'll take care of it. So when you log in, you're going to see these two folders. Just click on this one. That's the whole package that I wrote, especially for this tutorial. It contains all the slide codes and all the code that is in R Markdown files for you to run. And then you can open the project. It'll ask you whether the project is already open. So, okay. And pretty much all the code that went into the slides is under installation presentations. That's all the presentation codes, and then there are notebooks that you can run offline. I hope you guys know what R notebooks are. If not, it's like Python, it's Python Jupyter, this thing, where it's an interactive session that starts in your browser. You can run code, you can change code, everything. So you can there is a R notebook. There are a couple of R notebooks over here for you to play with if you are so inclined. Time. Okay, so that's what I said. You need to open that, and if Docker is not an option, then there is a link that is provided that you can go to and install all the packages manually on your box. But there are lots and lots of packages. Some of those packages have like native library dependencies, and they may or may not install correctly on all operating systems. So that's why Docker, it's just so much easier. So I've come to the end of part one, much earlier than I had anticipated. Any questions so far? Anything specific that you guys want to get out of it? I'm gonna break between each section so that I can get some questions out. Anything that you guys are looking particularly for in this tutorial? Any questions so far? Any concerns about the pacing of the tutorial? If not, we can move on. RStudio, RStudio. I'm gonna keep this as a reference for me so that I know where I am at. So let's move on to part two. This is going to be all about R packages. And if you have not really explored R's GIS packages, a fair warning, you will be overwhelmed by the end of this, right? Like you'll probably want to just get up and leave and say, let me just buy ArcGIS or whatever, and let me just do it in that. But it's very rewarding, because one of the things that is problematic with GUI tools, and I probably don't need to explain this to most of you in the room, but for people who are using ArcGIS or QGIS or what have you, you don't get that reproducibility, right? Like the one that you get with writing your own code is always reproducible. As long as your environment is pretty much stable, you can reproduce that same thing today, 1 month from now, 3 months from now. And you don't get that with a GUI environment. So that's why the proposition that you should use R for your geospatial visualization. And since you've committed to do that, you need to know what are the R packages that you have access to. So I have split this into 5 different sections. At the top, you see the CRAN task view. How many of you guys know what task views are, CRAN task views? See, yeah, I mean, there are a lot of R users, but nobody really knows what task views are. Task views are these extremely, what's the word? Aesthetically hideous web pages that pretty much vomit out all the R packages that can be found for that particular task view, right? Like I'm being extremely nice to task views right now. Trust me, I have a lot of things to say about task views. No, I mean, the people who write these CRAN task views are extremely, extremely talented people, and they have a lot of other things to do besides writing these task views. But the thing is that for people who are novice to a particular field, like if you are a GIS novice and you go to that CRAN task view, you will be completely confused as to where to start and where to end. Like it is just so hard to make out things. And at the same time, yeah, I mean, the HTML quality or the UX experience of these task views can be, bettered a bit. So CRAN task views are really nice once you have a good understanding of the ecosystem, so that you can always go back to them and figure out something that is amiss. But if you're starting out, CRAN task views can be really overwhelming. So no disrespect to the people who write CRAN task views. It's an absolutely fantastic resource that you should always go to. Just that, starting out, it could be a little challenging to navigate across the task views. So that's a link for analysis of spatial data for the CRAN task view. And now for the R packages, as I said, I've put them into 5 different categories: spatial data containers, packages that read data from external files, external databases, so forth. Spatial data operations, packages that operate on the data once you have that in R. Then the packages that are used for static mapping, and the packages that are used for interactive mapping. Now there is a somewhat overlap in some of these packages. You'll find certain packages can give you 2 or 3 of these functionalities, but there's not just one package that is going to do all of this for you. And that's by very nature of the design, right? You need packages to do small things and do them well, rather than just try to do everything. And then there are some other utility packages as well that we'll probably see. So let's start with the spatial data containers. By that, I mean packages that provide you data structures for holding data within an R session, spatial data within an R session. The first one that you will always invariably come across is the SP package, SP for spatial. This is almost like a 20-year-old package, still going really strong. It's a real workhorse for any vector data thing that you want to do with R. Like it provides you data containers for almost all types of vector data. The thing about SP package though is that it is not really aligned with the tidyverse way of working things. How many of you are familiar with tidyverse and the tidy data, this thing, right? Okay, good. So the whole tidy data ecosystem is all about the concept that Hadley came up with called tidy data, and you'll see a lot of the packages across various different domains. Like there's something now called tidy census, which is used as the tidy data for census APIs. There's something called tidy quant, which is used for quantitative financial analytics using that tidyverse, these things. So SP data is not really conducive to doing that tidy data manipulation thing. And it is in the process of being replaced by a package called SF. SF stands for simple features. So SF is going to be the future of spatial data containers in R. The thing though is that right now the things are at a crossroads, right? Like we haven't fully migrated to SF. SF is fairly new. It works really well, but it's still not adopted as widely as everyone. So if you were to pick up a book on spatial analysis in R, you'll find almost all the code examples in SP, right? So you still need to know SP. You need to know what SP looks like, what operations it supports. But then you also need to know what SF is so that you can like compare and contrast and figure out what works for your immediate needs. But always remember that you'll eventually end up going to SF way down the line. Then there is GeoJSON. GeoJSON is just a text-based container for based around JSON data for the geographical data. GeoJSON is actually, the GeoJSON specification is actually a subset of the simple feature specification. And GeoJSON format is really popular in web interactive mappings, right? Like whenever you see a map on a web page that is plotting certain data, chances are that data was sent as a GeoJSON to that map. So working with if you are working with web-based mapping, you will come across GeoJSON quite a bit. Especially for those of you who are aware of like the D3 ecosystem for mapping, it uses GeoJSON pretty much exclusively. And there's another thing I haven't written over here. It's called TopoJSON. So with GeoJSON, what happens is that whenever you have, let's say, polygon data, right? Like, let's say you have data about all the states of a country. With GeoJSON, every state data is represented on its own. So if two states share a boundary, that boundary is represented in both the states, right? It's unnecessary duplication. Not only is that, any operation that you carry out in one state, like if you want to move a boundary over here, you have to do that same operation corresponding to the other state that is sharing that boundary. So there is a lot of duplication of data, and the operations required to work on such a data is massive. So GeoJSONs tend to be quite big. So the original author of D3, he came up with a specification called TopoJSON. Topo stands for topology, which basically just means it is aware of the connectedness between these polygons. So if two polygons share a boundary, that is just represented once and referred to by both the polygons. So TopoJSONs tend to be really, really small in size compared to GeoJSONs. They are really good, but at the same time, from what I have seen, they're not really as much supported in geospatial visualizations as GeoJSONs are. So a lot of the times you'll see that the data is moved across over the internet as a TopoJSON, but in the browser session, it still gets converted into a GeoJSON before it is represented on a map. So it's just something to be aware of. WKB is like well-known binary format. So simple features is a specification that I'm going to talk about later. And it defines two formats, well-known text and well-known binary. Text is just a simple textual format that we'll see, and binary is like the binary representation of it, which is much more condensed, much more space efficient. So if you're moving data across, storing data on disk, WKB is a very useful format for that. I personally don't really work a whole lot with WKB, so I don't really know much about it, but it's, from what I know, it's really efficient. And lastly, the format called raster, which is used for raster data. So no matter what you do in GIS, when you get started, you'll see that data is particularly two types, vector data and raster data, right? Anybody aware of these, what vector data are, what raster data are? Okay, so if I have to quickly describe to you what a vector data is, if I want to draw a circle with a vector data, I'm just gonna say, this is the center, this is the radius, and it's a circle. That's the only information that I need to store. And the vector library or whatever it is going to figure out how to represent that circle within the memory, and when you're going to draw, it's going to draw on its own. The advantage of that is you can zoom that vector data to any resolution and it still says the same. Because it's just a set of instructions, right? It's just saying this is the radius, and if you zoom it, it just scales that radius accordingly. While as raster data is actual representation of the pixels involved. So it is actually all the pixels that went into making a map. So if you were to look at a picture, it's basically data about each pixel in that picture. And as you can imagine that when you zoom something like that, when it goes to beyond, when you increase the resolution, it does not have information for the more pixels that were added. So it needs to interpolate, it needs to extrapolate that information. So as you will see, like you typically see with these your digital photos as well. When you start zooming them beyond a certain point, they become jagged, right? Like the edges become jagged, the picture becomes unsharp. That's classic raster data for you. So, but raster data is immensely useful for things like satellite imagery, LIDIR, information that is much more easily representable as a raster format rather than vector format. Because if you were try to represent satellite imagery as a raster data, that format will be huge. Like it will be just unmanageable. While as raster, it's at least manageable. Sorry, I need to keep on referring back to this so that I don't get lost. So once we know what are all the spatial containers for GIS, let's look at some of the ways that you can bring in data into the R session from external sources. Because a lot of the times, that's what you're going to do, right? Like you're not just going to generate the data within your R session. You will, but you're also going to interact with data that is stored outside of R. So these are all the packages. As you can see, so many of them. Just to quickly start with, RGDAL and GDAL utils are, it's like, GDAL is a C++ library that is used for pretty much interacting with any kind of spatial data that you can think of, like any kind of spatial data stored in a file or a database that you can think of. If you have GeoJSONs, if you have useR shapefiles, if you have data stored in a database, like it just literally has drivers for pretty much every format imaginable out there. I think it's like 200 formats or something. It's just ridiculous. So it is a one way to interact with any kind of spatial data out there that is written in files, be it in database. And RGDAL and then a helper package called GDAL utils are the interfaces for that. So you will see RGDAL quite a lot. Like either you'll directly interact with it if you're working with SP data, or indirectly interact with it if you're working with simple features, but it's just gonna show up everywhere. GeoJSON.io was a project, is a project by R Open Science that is used specifically for reading GeoJSONs and TopoJSON files. You don't really need to use GeoJSON.io. Like RGDAL is perfectly capable of reading GeoJSON files, but GeoJSON.io provides a little bit help in that it's not dependent on an external library like GDAL is. So if for GDAL, if you have a limitation of like not being able to install a GDAL library, then GeoJSON.io can still be used for at least reading and writing GeoJSON data. Another very popular data storage format for spatial data is like the NCDF4 format and a related RHDF5. But to be really honest, I think NCDF4 can encode data in HDF5 format as well. So I'm not really completely aware of all the distinctions between the two, but you will see that a lot of the times the multidimensional data that you see, like climate data, like ecology data, data that spans time dimensions, data that spans maybe multiple bands of a satellite image, those kind of data where you have multiple dimensions, be they time, be they a band of a satellite image, they tend to be stored in NCDF, RNet, CDF, RHDF formats. These formats are highly specialized, highly optimized. One of the advantage of these formats is that they don't necessarily always read all the data at the same time, completely in one shot, which is really useful when you have like a file which you could easily have like a 1 gigabyte file, which is NCDF, and you might be interested in only working on a subset of that data. With these formats, you can do that. Like you can open these files and read only the subset of the data instead of having to load the entire file into the memory, which saves you considerable amount of memory. The fourth option is basically when you have data stored in external databases, PostGIS, which is basically an extension to a Postgres, which is a RDBMS SQL database. It is probably, I would say, the #1 choice for storing spatial data in databases. There are a lot of other options, like even MySQL has a GIS option, a lot of other databases, but PostGIS is probably the #1, right? So our PostGIS and PostGIS tools can read-write data from PostgreSQL database. For those of you who work with QGIS, which is a GUI tool for working with spatial data, just like ArcGIS, the open source equivalent of it, there is a package called RQGIS, which allows you to interact with this QGIS. The QGIS is not just a GUI tool, but it has a lot of algorithms that are implemented as APIs, Python APIs, and RQGIS can be used to actually call those algorithms. These are like spatial analysis, all sort of stuff. So RQGIS is a really nice tool for that. And there are another two sets of GUIs called Saga and Rgrass, which are again, like you can use Saga and Rgrass, or Saga and Rgrass 7 for these tools. If you use them, just be aware of these toolkits. Get Landsat is a newer package that I saw, which has like amazing amount of Landsat data, LIDIR data. If you are doing that kind of analysis, Get Landsat is your one place to go. Like it'll just pretty much give you a lot of LIDIR data by just calling simple APIs. The last thing is more, the second last one is more US centric. The Tigris, Tidy Census, ACS Census APIs. These are packages used for accessing US Census Bureau's data. Pretty much everything that is Census Bureau related you can access from here, and like historic data going back all the way to the 90s or 60s or something like that. The reason I show that is because there are certain other data for other countries' census as well, like you have the last three for like Australian and UK and some other census countries. If you are working in a country and you have access to the census data for your country, and let's say after the end of this talk you're completely motivated and you want to write a package of your own, and let's say you have access to census data of your country, take a look at these packages as to how they do that, right? How they provide access to the American census data. That might be an incentive for you to write your own package for the census data of your own country. So packages for spatial data operations. Okay, there we go. The three that I always end up using, and you'll probably end up using quite a lot if you're starting out with GIS, are like ArcGeos, GDistance, Geosphere. Basically, they allow certain geometric, topological calculations on data, right? If you have a bunch of polygons, what are their centers? If you have certain polygons and certain like points, yeah? I am not, but I will find that out for you. Sure. So this is basically just carrying out spatial operations on data, right? Like you want to know the centroids of polygons, you want to know whether certain polygons intersect with other polygons, or what is that intersection boundary between these polygons, whether certain points lie within certain areas, all that sort of stuff. You can do that easily with like the first three. SPATstats and SPDEP are like for people who are into spatial modeling. If you're doing a lot of like spatial modeling, point pattern analysis, bunch of other techniques. Then SpatStat and SPDEP are like the to-go packages to get started with that. I haven't really listed all the packages which are available for very specific field. Like there are packages that allow you to do ecological modeling. There are packages that allow you to analyze LIDIR, Landsat data. There are packages that will allow you to do archaeological modeling. I haven't put them over here because that is like, that gets really specialized, and I wanted to keep this as generic as possible. But yes, there are options for that. Spat graphs, a lot of the time spatial data by its very nature is graphical in nature. You have like edges and vertices that connect to each other. So Spats graph is a tool that allows you to use graphical analysis on top of your spatial data. Map tools is again, I should have probably put map tools again at the top with those three. It has a bunch of operations for like combining spatial data. You'll end up using quite a bit. If you're strictly working with GeoJSON data, our Open Science has these two tools called LON and GeoAxe, which work really well on geospatial on GeoJSON data. Spatial.tools is used mostly for, is it spatial.tools? Yeah, I think it's spatial.tools. It's mostly used for working on raster data. Like any operations that you do on vector data, pretty much similar kind of operations that you can do on raster data and a lot more. And finally, as you guys might be starting to use the focus is on getting a very quick map or a very quick output, right? Often at times you'll find that certain geometries, when you're trying to plot them, are really complex, like certain polygons, the boundaries of a country. They can be really complex, and their corresponding shapefiles can be really big. And ergo, the rendering that you do, the plot that you make, it kind of takes a while. So there's a very good package called RMap Shaper, which simplifies those polygons. And even a simplification by a factor of like 0.1 or something reduces the size dynamically, right? Like it just drastically drops the size, and that allows you to just build your maps much more faster. So RMap Shaper is something that I always end up using whenever I'm doing any kind of like exploratory analysis to just simplify anything. Maybe when I want to like plot it in a production thing, I might not use it because there I need those detailed features, but when I'm doing just basic analysis, RMap Shaper is a lifesaver. It really reduces the mapping time quite a bit. So look at that. Finally, coming down to the two most important ones, the ones that you are all here for mapping. The packages available for mapping, so static maps and interactive maps. I'm not using the word dynamic map as opposed to like static maps. I'm using the word interactive map, and the reason for that is the way I define dynamic map in this context is a static map that you can change dynamically, right? Like if it's a map that you say, okay, now plot this, and you destroy that map and draw it completely with the new data, I call that as a dynamic map just simply because it allows you have that flexibility to change the parameters that go to that map and change it dynamically. And we'll see some of that, how to do that using like Shiny and stuff. While as an interactive map is something that a user can actually interact with. Like you can click on things, you can hover over things to get more information, you can dynamically select what needs to be shown, what doesn't need to be shown. So those are interactive maps. So static maps, there's a package called cartography which allows you to build various types of map very handily. We're gonna explore all of these in detail, so I'm not gonna probably talk on detail on each of them. But if you are just getting started and you want to build something out quickly, I would absolutely recommend you take a look at the top two ones, cartography and TMap. They are probably the quickest entry point into building maps very quickly. But then as you come down, like the ggplot2 ecosystem is huge and extremely powerful. How many of you know ggplot2? Oh, everybody, awesome. So if you already know ggplot2, just go with ggplot2. I mean, it's just the power that you have with ggplot2, nobody else is gonna give you that. Choropleths are specifically for plotting choropleths. It's a very handy package for that. RasterWiz is mostly used for raster data visualization. It is an extension of ggplot2, or rather there is a way of extending ggplot2 plots with RasterWiz. And then finally, if you want to do certain animated maps, then you can do GG animation or animation toolkits. Again, fairly easy to use. Even if you haven't used them before, even if you look at one example, you'll figure out what needs to happen. And do note that I've put animation packages under static map, because even though their content changes, it's not part of an input, right? You're just build up a loop that just goes on and changes your map like a GIF does. So I'm still calling it as a static map. A little bit of schematic differences, I suppose. And then interactive maps, right? If you already know ggplot2, there are certain packages that allow you to make a ggplot map interactive, which is probably much more easier for you to get started if you want to build interactive map. One of those packages is ggiraf. It's for adding these small effects to a ggplot2 map. You can add hover effects, you can add click effects, you can do like tooltips which show you information as you hover over the information. So ggiraf is really nice. I like that because if I already have a ggplot2 map, I just want to see it explore it a little bit more, I can just pass it through ggiraf and be done. Leaflet and the Leaflet ecosystem, like the other packages that I mentioned over here, that's basically the bread and butter of web mapping all day long. Like you can just take that and go completely nuts as far as your imagination takes you and build extremely powerful web-ready maps. In fact, most of the maps that you see, most of the interactive maps that you see on websites most of them are like Leaflet. Like they are based on Leaflet packages. So yeah, I mean, if you know Google Maps, if you've looked at Google Maps, Leaflet is just exactly like that, but it's open source, it's free to use, everything. MapView and MapEdit are like really specialized packages, mostly for interactive data analysis. So for people who want to do modeling, who want to just like basically have a quick look at the data that they have, not spend a whole lot of time on it, MapView is really ideal for that. It's built on top of Leaflet and some other visualizations, but if Leaflet, you find Leaflet like extremely challenging and extremely hard to get by, MapView would be the easy wrapper on top of it. And it has a bunch of other features as well. So let me not just say that it's a wrapper on Leaflet. And MapEdit was literally released 3 or 4 days ago. Anybody heard of MapEdit before? Yeah, I just one guy. Yeah. So it was literally released 3 or 4 days ago, but I think this is going to be like probably the future of interactive visualization because it allows you to change maps on the go in the browser and get that data back into your R session and do that back and forth, right? So you can like make changes in R session, send it back, do some visualization adjustments, get that thing back in, and keep on doing that. And then 3 other packages which are specialized are called RBouquet, Plotly, HighCharter. The advantage of these 3 packages, just like the advantage of ggplot in the previous system, is that they are generalized plotting libraries. You can not only plot maps, but any kind of data, like your regular bar charts, pie chart, whatever you want. So these are really nice as well. Like if again, Leaflet is going to be really, really extensive, but if you are overwhelmed by it to start with, look at these 3. They have much simpler APIs to build maps. I'm going to quickly conclude this. The last section is odds and ends packages. Sometimes you really don't need to plot map data on an exact map. There is a term called cartograms or tilegrams. We'll see some examples of that if you haven't really seen that. But basically what they do is they distort the map areas based on a certain proportionate value that you're trying to map. And this sort of allows you to build maps that are probably better representative of the underlying data than simply representing the underlying population density. So we'll see some of those. Our Natural Earth is a very good source for getting vector data for pretty much everything on the Earth, right? Like there is a project called Natural Earth Data, and our Natural Earth Data is basically a wrapper for that. So if you want a map of US boundaries, it's just one call. Like our Natural Earth, get country US, and the level should be like state level or county level or what have you. So it's a really, really powerful package to have in your arsenal. US maps and Albers USA maps are like pre-packaged packages that give you much better USA maps than what you'll see with like typical Mercator projection. Like if you go to Google Maps and you like zoom out all the way to see the world map, you're going to see Alaska, which is so huge, and Greenland, which is so huge, but they are really not that huge in real life, right? That's just because of the projection that is used. So like US maps and Albers maps is a better alternative for that. There is like lots of packages for working with Google Maps and Google Maps APIs and the KML format that Google came up with. I've listed all those out. They have certain overlaps, but some of them provide very specific features from the Google Maps ecosystem. So you may end up playing with all 4 of them at certain point of time. And finally, OpenStreetData. I hope everybody knows what OpenStreetData is. Anybody who doesn't know what OpenStreetData is? Okay, good. So OpenStreetMap and OSM map data are like the packages that you'll use for getting data out from OpenStreet. So you don't really need to go to the website and download stuff. Just do it from package. The whole idea behind providing all these packages to you guys is that you can pretty much do all of these activities from within an R session. You really don't need to go outside of your R session to get data or to plot data or to do all those things. You can literally just be in that R session and do everything from there. Just the challenge is to figure out what these packages are and what functionality they provide. So let's see. Now I'm going to walk through the spatial data structures that you have in R, right? You saw the SP package, you saw the SF package. We are going to explore those in a little bit more detail now. Anybody bored yet? Anybody jet lagged, want to sleep? Yeah, sorry, one thing I should say is I don't do memes, right? Memes. I absolutely hate these slides where there are just memes and people have just memes and memes and memes. I don't like to do that, right? I'll try to make a funny joke once in a while, but yeah, you're not going to find any memes over here. Okay, so, yeah? Sure. Yeah, RStudio. All lowercase. Yep. So, if I have to say, just define data structures for spatial data in R, the two most commons are vector data and raster data, right? Like most of the time, that's all you really work with. Like you have vector data, you have raster data. Then you have like spatio-temporal data, which is still a form of like either vector or mostly raster data, but there is that added time dimension to it, right? Like if you have taken satellite image every day of the day, then that's a raster data, but then you have that time dimensional aspect to it. Or there could be multi-dimensional data, like if you're taking infrared photography or maybe satellite imagery, then the satellite image itself has like various bands, and those bands are now like your multiple dimensions of your raster data. And you can do analysis at like individual band level, or you can do analysis at a combined band level. So these are basically, that's basically it. That's the nature of spatial data in R as far as I am aware. And please be mindful that I'm only like just 2 years into GIS, so I'm not like completely aware of all that there is to it. But to get started with, this is all you really work with. So SP package is basically contains S4 classes. How many of you know what S4 is? Okay, some of you don't. You don't really need to know about it. It's just basically an object-oriented way of representing certain information. So if you have worked with any other programming languages and you know the concepts behind object-oriented programming, that's what it is. S4 is a class that you can use to store data. So SP packages are basically S4 classes that mostly represent 2D vector data. That's a little bit of a simplification. You can actually have multidimensional data over there, but for most purposes, you can just say that it's a 2D vector data into that SP package. So what's a 2D vector data? You can have lines, polygons. So what you see over here are the actual classes that are available in that SP package. And so that's just basically the geometry, right? Like when you say it's a line, then that's it. Where does it start, where does it end? Or if it's a polygon, what are the vertices? That's all. But you can have certain attributes attached to these geometries. So to store those attributes, you have the spatial, before we go on to the attributes, there is a difference when it comes to lines versus a spatial line or a spatial. When you say spatial, you sort of add coordinates to it, and you add a coordinate reference system to it. So that's what makes it spatial. That's what allows you to plot it on a 3D surface, such as our Earth, right? Most of the data that you're working with will be Earth data. So from 2D geometry to 3D geometry, that's what spatial gives you. It allows you to represent a data that is typically on a spheroidal surface or a geoid surface on a 2D surface by adding coordinate reference systems to it. We'll see a little bit more of that if that confuses you. And then finally, as I said, you have certain attributes that are attached to it. Like if you have county, what is the population of that county? If you have certain forest region, how many trees are there per square mile of that forest region? That sort of data, that's called attribute data. Those now get into the data frames. So if you already know R's data frames, spatial point data frames, SPDF, I shortened the name for it, but like you can easily make out what that stands for. Like SLDF is spatial lines data frame, SPODF is spatial points data frames. But what you really need to remember though is that although they end with data frames, they are not really data frames. They do contain a data frame, but they are actually S4 classes. And that kind of matters a lot because you might try to be tempted to treat them as a data frame and try to work with them as data frames, and there are places where it will not work. There are places where it does work, but a lot of times it doesn't work. So you need to know that they are not really data frames. RGDAL read OGR is basically that one function that will allow you to read external data that I showed you in those various file formats and database into SP objects. And RGDAL is just basically so powerful that you can say read it from a GeoJSON, read it from a PostGIS database, read it from a E3 shapefile. It can read all of that and give you that same SP representation as long as that's the exact same data that is stored in these different formats. So RGDAL read OGR gives you an SP data. As I said, SP is not compatible with the tidyverse way of things, and SP operations compared to the simple features operations can be slow, and I'll talk about that as to why those can be slow. I should have bought a... And as most of you are going to use ggplot2 or already using ggplot2, one of the things you need to be aware is when you want to use SP data and plot that in ggplot2, there are certain things you need to do before you can plot that data. You can't really just take a spatial polygon data frame and plot it in ggplot2. You can, but it's not that easy. So we'll see how to do that. So now we are going to start looking at some code, okay? So like feel free to interrupt anywhere, feel free to take pictures, but you have access to all of this in the GitHub repository that I've shared, so you don't really need to do that, but if you want, you can just ask questions as any time you want. You load the SP package. Most of the time I've used suppress package startup messages just simply to avoid a lot of unnecessary output on the slides, but like if you're playing with it, if you have that, just call library SP without that suppress thing and see all the messages that it outputs. You'll be amazed at the kind of information that it shows you when it starts up. Like what are all the other, what's the system that is running to, what's the GDAL library that it's linking to, what's the RGOS library that is linking to. It's kind of interesting. We use that quite a lot when we are trying to debug issues around things. So there is a data available called, I don't even know how to pronounce it. I'm just going to call it Muse. I think that's what it is. It's basically soil data from Norway. That's what it is. And it's just a classic data frame, right? That's all it is. So how do you make that spatial? You can see the columns. It's all basically attribute data. X and Y are actually the latitude, longitude, or rather the longitude, latitude for the data, and then bunch of concentrations of cadmium, concentrations of various minerals in the soil around certain points in Norway. So, and you will see this data set used very frequently in ArcGIS world. It's one of the go-to data sets for visualizations. So the first thing you do is you say that the coordinates for these data sets are X and Y. That's the formula. For those of you who are very familiar with R, the tilde is just basically saying that it's a formula, and it just sets those coordinates. So at that time, it becomes a spatial object. It's no longer a classic simple data frame. It has become a spatial object. But at the same time, you also need to indicate what is the projection that is used for representing the values of the coordinates. What's that string? You don't need to know, but if you are working with data that comes externally, like this, comes in a data frame, not in a SP object, and you need to convert it into this thing, you need to know what that string is. You cannot simply know, looking at a bunch of values, what is the projection. You have to know that as a side effect of working with that data. So I already know that this data is using that projection. For those of you who don't know what projections are, I'll come to that. Just keep this point in mind. I already know what that projection is and how is it represented in that string format. So that's what I'm doing. I'm saying that this is the projection used for this data. And now if you do class mesos, the earlier was data frame. Now if you do, you'll see that now it's a spatial points data frame. So at this point, you know that it is storing spatial points, XY locations, and it is a data frame because it has a lot of attributes into it. And though the attributes you've already seen. So the first thing you'll probably do when you do something like that is just plot it out quickly and see what it has. So if you just call plot is basically S3 generic method, S4 generic method that it figures out how it should plot the object based on what object it is passed to it, right? Like I passed a bunch of points, so it knows that it has to print points. If I had passed in a spatial polygons data frame, it would have plotted polygons. So plot is really flexible that way. I just put a box around it and gave it a title. That's like the simplest way of plotting SP data. And you can clearly see that there are points over there. Not really that interesting, but you know how to work with that. So that was basically reading a data frame and converting it into an SP object. What if I already have data that can be read directly into an SP object without having to go through that process of setting the coordinates and giving it the projection string? So that's where you have that rgdal read OGR, that's the highlighted function over there. It's basically reading that file called scott.bng from a data from file system. I have given 2 calls over there which I have commented out. If you do get a chance to work on this code, just uncomment them and run, and you'll find some information. You'll know what it is later on as we talk. But right from the get-go, you get to know what is the container for that. It's a E3 shapefile. Where is it located? You see the file name. It has 56 features. Features are like your shapes, your polygons, your points, whatever that is. Since this is a spatial polygons data frame, as you see below, then that means there are 56 polygons. And as 13 fields means 13 attributes data to that value. So that's basically a spatial polygon data frame. Yeah, so that's how SP objects are essentially. You use rgdal read OGR for reading them, and they are specific classes for each different type of geometry. So one of the limitations of SP is that you cannot represent mixed geometry in a single SP object. You cannot have an object which contains points and polygons both at the same time. That's just the limitation of how SP was designed, right? You have spatial polygons data frame, you can have spatial points data frame. There's no such thing as spatial geometry data frame. So before I talk about the SF package, the successor to SP, let's look at what simple features mean. Simple features is basically a 2-part OGC, which is, I think, Open Geospatial Consortium or something like that, an ISO standard for like common storage as well as modeling of 2D geometries. That's what simple features is. The part 1 of it defines the hierarchy of classes and their binary representation. So well-known text and well-known binary, how to represent geometries using these 2 formats. That's what that part 1 specification is. So for example, if I want to represent a polygon in well-known text format, that's what it is, the 3rd line. It's so simple, straightforward. I just tell you which all the polygons are. The first point is the starting point, and you move subsequently. I think the way it moves is, let me double check. Yeah, you always specify the outer polygons counterclockwise. So the next point is the point that is going to go counterclockwise. And if you have holes within those polygons, you'll define one more polygon within that, and I think that one goes clockwise, something like that. There's some specifications over there. But the thing that you'll find out is that even though there are 4 points in the polygon, there are 5 points defined in the actual call. That's because the 5th point is the exact same as the first point. That's the requirement of the specification. The polygon needs to be completed on that point where it started. And you have similar representation for lines, for basically all the simple geometries that I showed you, like lines, shapes. But it also has like other features like curves and triangles and a bunch of other things, which we are not going to deal with in this tutorial. But I highly encourage you to look at spatial features specifications at some point of time. And the part 2 defines the SQL interface, the SQL query language that you can use for accessing that data. So if you like use R PostJSON, stuff like that, they are working off that specification for accessing that data via SQL queries. And I don't claim any credit on coming up with any of this. All of this came from the Wikipedia entry. So like if you saw this exact same thing on Wikipedia and say, you know, like I've given a disclaimer for that. Where are we on time? Okay, just running a little over. Let's see. So SF package is the implementation of the simple feature specification that I talked about. And the good thing about SF is that instead of like dedicated S4 classes, it just is your regular data frame that all of you know and use every day in R, right? It's exactly that. It's a data frame, but it has a very special column called the geometry column, which is basically nothing more than a list column. How many of you guys know a list column is? Okay, some of you know. For those of you who don't know, most of your typical columns tend to be, what is known as, what's the word? A single value, right? Like you know, X is 10, 20, 30, 40, whatever. It's a single value, be it character or a string. A list column is basically a column which contains lists. So each value is a list of other values. That's what a list column is. It's so simple. I mean, like, when you look at it and when you get it, it completely blows away your mind. Like, wow, this is so easy. I mean, that's just like, wow, I get it. Like this, believe me, like understanding SF is much more easier than understanding SP. SP takes a little effort to understand. SF is like, I know data frames, I know list columns. Intuitively, I've looked at tidyverse. I know SF. That's it. And another thing that SF does is that it's really quite fast compared to SP for a lot of spatial operations, starting from reading and writing data. So sometimes I've seen like it takes like 30-40 seconds to read data in SP, and it's like 2 or 3 seconds flat when I'm reading it in SF. So even starting from that point up to operations, it's really fast. And now I think the last version of SF got features for spatial indexes, which are very specific data structures which allows you to access data even much more faster. People who know RDBMS should be familiar with the concept of indexes. That's what they are. And with that, it's just blazing fast. That's what the word I would use. And SF plays really nicely with ggplot2. So you'll see that I'm going to show you plots where this is the code for plotting with SP and this is the code for plotting with SF. And look how compact that code for plotting with SF is. Another advantage of SF is that you can represent multiple geometries in the same SF object, because it's a self-describing format. So you don't really need specific data structures as you have in SP for SF. You can store multiple geometry in that same SF object. The simplest thing to remember about SF is all functions starts with ST. So even if you don't know anything about a package, just hit ST underscore and hit tab, and you'll see all the options that are. Those are all the functions that SF has to offer. So even if you are wondering, how do I calculate centroids of polygons using SF? Just hit SF tab, you'll see one of the options as centroid, the ST tab, and then that's this thing. SFG is the geometry of a feature which represents the actual geometry, one of the things that I showed you in the previous slide. SFC is the class of the column that stores that geometry in a data frame, the list column, right? And that's about it for SF. Like that's really it. It's so simple and so straightforward and so beautiful. There's a lot of things that are behind it, right? Like I'm not trying to simplify saying that SF is a really simple thing. What happens behind the scene is tremendous, but the interface that you get to work with is amazingly simplified. So how do simple SF objects look like? I'm not going to show you how to construct an SF object from the get-go. I'm just going to show you how to read it. So in SP, you were using RGDAL. In SF, the good thing is you don't need to go to a separate package. You just read it from the SF package. SF ST read, and the arguments are pretty much the same that you'll give to RGDAL read. What was that? RGOS read RGDAL, right? So you'll pretty much read OGR. Sorry, you'll pretty much have the same exact arguments. And when it reads, it's telling you that it's that file that it has read from that location. It has 13 fields. It is multi-polygons. What are the dimensions? Like, what are the fields for dimensions? What is the bounding box? Bounding box is basically a area that encompasses the minimum area that will encompasses all the data of your spatial data structure. That's a bounding box. And what's the proj4j string? So again, projections, I'll talk about a little bit more detail, but it tells you all that information. And if you do names SF, this is exactly like doing names on any data frame, and it's going to show you all the columns there are. And as you can see, like, these are exactly just like your regular data frame columns, except pay attention to the last column, which is called geometry. That is the SFC data type column that I talk about, which stores the geometry associated with that. So how does raster data look like? Raster data has basically 3 classes: raster layer, raster stack, and raster bricks. Certain more, but these are the starting points. Raster layer is basically that one single layer which contains data for raster, right? So if you have like a pixel, you'll represent maybe like 20 by 20 pixels, so 400 pixels at all in total. You'll have 400 cells for that, which tell you, and there'll be a value associated with each of those 400 cells. That's basically your raster layer. Raster stacks and raster bricks allow you to like have multiple of these. Out of this, one of the formats, I think it's raster brick that supports multiple files, while as raster layer still supports just a single file, but multiple bands. Fine minor distinctions that you need to be aware of when you start working a lot with raster data. In fact, I don't work a whole lot with raster data, so I'm not myself an expert on a lot of this stuff. The raster data you read from the raster package, just raster system file, external, raster this thing, and then if you see class, it's a raster layer. That means it has just that one layer, and it has like values for the cells. So if you plot a raster data, like I did, you're gonna see the pixel, color values that you saw. But the good thing is you can plot raster data and vector data together, right? What's the point if you cannot plot your raster and vector data together? So the next line, what I did was I added the message data set which had those, the points on top of the raster data. The argument add equal to true means don't generate a new chart, just add it to the existing chart. And the box and title is just for this thing. So this is basically one of the ways you combine raster and vector data together. So that's part 3. Any questions so far? Too fast, too slow, too confusing, too boring? I will say that this talk will be, it'll give you a lot of options, right? It'll just open up the world of geospatial visualizations in R. Even if it tends to overwhelm you at points, just move on past that point and just go to the next thing, just make a mental reminder, come back, read the documentation. One of the nice things I'll say about all these packages is that they are really well documented. Once you start reading package documentations, you will find a lot of the informations to the questions that you will have. So even if like some of the things over here feel kind of like unintuitive, just go with it and then start reading up on these later on. So now we saw what were the data structures, how do you read into those data structures. Now how do you work on that data, right? What typically do you do with that data before you plot it? How do you make it ready for plotting, or how do you modify it for plotting? So as you can see, our message data set has 155 points, and for each point there are 12 attributes that are stored. So if I want to simply select the 9th and 10th point, I select it just like I would in a typical data frame, just with rows and then columns. So I'm selecting 9th and the 10th point, and I'm only interested in the lead and the zinc matrices out of all the other minerals. So that syntax should be very familiar to you guys. It's just how you do it with regular data frames. And the result is again a simple spatial data frame, but it's a subset of that data frame. So that's basically subsetting. The last row, I apologize, got cut down. The output was a little more. Maybe, yeah. So that is basically just filtering data, right, on a certain criteria. So I'm just saying, okay, how many rows have I where the lead count is more than 75% percentile? And it'll show you what that is. Like, it'll give you a data with only the rows which have the lead count more than 75 percentile of the maximum lead count. So basically, if you are used to working with subsetting and selecting data in data frames, you can apply that to your features. The trick is if you are like fairly new R user and have extensively dealt with only dplyr and have not really dealt with these kind of operations before, you are in for a little bit of surprise, because as I said, SP doesn't really work with tidyverse data frame. So if you were to like take this call and convert it into a dplyr filter call, or if you were to take that upper call and convert it into a dplyr select and filter, whatever is the other this thing call, it's not going to work because SP and dplyr does not work. So you have to use like the base R way of subsetting and selecting data. So that's just basically like selecting that. What are some of the other operations would be like again, the double bracket operation for getting data for a single column that gives you all the data for that single column. Proj4j strings, getting setting. If you want to transform data from one projection to another, that's SP transform. You'll use that a lot, trust me. Get used to SP transform. Geometry tells you what is the geometry of that data. And then a lot of the times you're interested in finding out, do these set of points fall within these certain polygons or not, right? So that's where you have, like if you have a driving record of, if you take a long road trip across Europe, now you want to know which are all the countries where you took this thing. You have these points where you have taken your road trip. You can then give a set of polygons that represent Europe and say, okay, you know, do any of these points go through Britain? Do any of these points go through Belgium? Whatever. That's that over operation. It's much more powerful than that. I gave a very simple example, but over is a very powerful way for like doing this kind of intersection kind of things. And finally, these are dedicated packages: RGOS, GDistance, Geosphere, map tools. If you work with SP data, you'll end up working with this. Like there are operations over here that you have to use at certain point of time. So, you know, it's just a matter of reading the documentations for these packages. Some of them have overlaps, but some of them are like very specific to functionality they provide. So here's a simple operation. That Scott BNG database earlier I told you about was a polygon data for Scotland. Now I just want to know what are the centroids of each of the regions of that Scotland, these things. So you can see RGOS G centroid, I pass in the SP, the polygon, and what I got was the location, the spatial points data frame from a spatial polygons data frame, and where that each point represents the center of a polygon. And those are again plotted on that same map with a black dot. It's that easy, right? It's that straightforward. SF data, if you are familiar with data frames, if you are familiar with dplyr, SF is just exactly like that. Like dplyr works very easily for SF data. Right now I haven't shown a dplyr way of selecting, but you can easily replace that call where I'm saying the third line in the code, you can easily replace that with a dplyr call. The trick over there is st as SF, because a lot of the times when you're working with like legacy code, you'll see SP objects. If you want to start working with them in SF objects, just call st as SF on that SP object, and you're going to get a SF object out of it. So that's a call which I use quite a bit. And then st coordinates gives you coordinates, just a bunch of other calls that tell you much more information. St geometry will be very useful for plotting because it gives you the raw geometry that you need to plot. So st geometry is really useful. Just run methods class SFC, you will see all the operations that you can do on those SF objects. So here's a slightly complicated example. Essentially what I'm doing is just to start with albers USA.USA SF, that just gives me a ready-made SF object from that albers USA package, which has the US map and the Alaska and Hawaii, moved down there for better representation. So I take that, I transform it to a projection that is more suitable for the Northern America region, and that projection is called, equal area something projection. Don't really need to know the exact details of it. If I wouldn't have done that, the top curvature that you see, that really nice curvature, it would have been like a big straight line, and the map would have been more wider than it really needs to be. So that's basically transforming it into a projection that is needed. Then I find the centroids of it. Once I find the centroids of it, I subtract 50% of the polygon from the centroid. So I'm going to walk over here. If everyone can hear me, I take this point, I subtract 50%, I subtract the boundary of that polygon, each boundary from this point, and then multiply it by 50, so basically the distance is 50% of the original distance, and create a new SF object out of it, right? So that's the inner polygon. And see the code, how simple that is. I mean, even if you don't know a whole lot of math or geometry, it's fairly straightforward. The subtract, multiply by 50, and then add it to the center, and that gives you that new this thing. So I plot that, I plot the center. Typically, what's the point of doing something like this, right? Like, why would you want to do this? This is just for showing you right now, but there is a mapping technique where sometimes what they do is they will resize this area, the inner polygon, based on a certain parameter, like maybe the population of that state or the GDP of that state, to better represent that information. That's one of the techniques that I see being used. So that's something that you can use. So it's fairly easy to do with SF. Operations on raster data. Again, I'm not a big expert into raster operations. I'm not a big expert into GIS to start with, but raster is even this thing. You read the raster data. One of the good things about raster data, as I said, is raster data can be huge. Like it can be like not just megabytes, but gigabytes. A single file can be gigabytes in size. So you really, if you are working with raster data, you don't really need to read all that into memory, and that's what it is. Like if you look at the third call, it's in memory is false, means that data is not completely loaded into memory. It will be loaded on an as needed basis, which allows you to have much more faster operations. It has just a single layer, and it is 115 by 80. That's the size of it, and it has one value. So that value is like whatever if I call cell stats on that, it tells me the minimum of the value that is stored is 128, maximum is this thing. So it's basically just working with a single dimensional vector. That's what it is, right? That's that value in that raster data. It's just one dimensional vector. A very simple example over here is there is a function called calc, which allows you to apply functions on the raster values, similar to like the sapply functions that you might have seen, sapply, lapply functions, or the dplyr mutate functions, map functions, those kind of things. So here, if I see the plot of those values, I saw that it was like right skewed, it's not normally distributed, and I just wanted to show some example for you guys. So when you see typical not normally distributed data, one of the things you can do to normally distribute it is just to do the log transformation, right? So that's what it is. It's basically just doing a log transformation on the data, and now you see that the data is much more normally distributed. There are tons of other operations that you can do on raster. This is just like probably the simplest of ones that I've shown you. In addition to that, you have rQGIS, which allows you to access a lot of spatial operations via QGIS. You also have rQGIS allows you to, and rPostGIS and PostGIS SQL. Why do I mention this? Because sometimes it is more efficient to do the processing at the data storage layer than bringing in the data into your R session and doing it over there. Like if you have data in a Postgres database, PostGIS database, and you know how to work with PostGIS SQL queries, you can do some of these operations directly into the database, which is probably going to be much more faster than bringing all that data into R and doing it into R, right? So that's why if you work with PostGIS, just like look at these tools so that you can modify the data in place. So we are at 10:45, and we break from what, 11 to 11:30, is that it? So how about 15 minutes for this section? I had a 5-minute break, but I'm just going to continue unless there are objections, so that I can give you all that 30 minutes to debrief. This is going to be a very interesting session for anybody of you who's interested in presenting data in papers, in published journals, in web pages which are going to be accessed by end users, right? Like production quality data. How do you put that from R? So that's what all this whole thing is all about. Obviously, the first thing you do is display the data in your R session when you call that plot or whatever. You can save that data into static images. If you don't know much about how image formats works, just remember that JPEG is lossy. So that means that once you've stored information in JPEG, it is a lot of information has been lost and you cannot ever recover it. So as long as you know what the limitations of your JPEG are, It's fine to use, but it's a lossy format. As opposed to that, BMP, TIFF, PNGs, those are more or less lossless compressions. So if you store the data over there, you can reprocess them again and again without really losing data. TIFFs can be really used, like uncompressed TIFFs can be really huge. So if you are working with TIFFs, again, something that you need to be aware of. So JPEGs, if you want to output JPEGs, those should be the last of your operations, right? Once you have put that data in a JPEG, you can never really work with it again. You cannot give it to Adobe Acrobat person, Photoshop person, and he can recover anything magical out of it. Like it's just not possible. He'll scream at you. So you want to store that data in a TIFF or a PNG or a BMP. Another format is a vector format. So the upper ones were raster formats. It just stores pixel values. The SVG is one of the popular vector formats. There are some other ones as well. SVGs are really nice. I personally tend to like SVGs when I'm outputting anything that needs to go on a web page because they can be scaled infinitely. They look really, really well. I'll show you on the next slide. And it's a popular, SVG format is now supported by pretty much every modern browser out there, except for those of you who are still using IE9 or IE10. How many of you using IE9, IE10? Nobody? Okay, good. If you are, I mean, since I'm in information security, I would say you'll get hacked before you have to worry about any of these things, right? So you have more things to worry about than SVG not being supported. And then if you want to make animations for like spatiotemporal visualization or visualization of something that is, like over a set of images, you can save that as a GIF or MP4, which is like a video format, and it'll autoplay in your browser. So that's an option when you want to show animations. So this is basically all about like saving data to disk. Another option is you want to show that into your end document, right? PDFs, Words, HTML, that sort of stuff. So that is basically, it's still saved on a disk, but it's now embedded. It's now not exactly embedded, but it is available to be shown inside your documents. Like I think in case of PDF and Word, it is actually literally embedded in that document. HTML is mostly like it just refers to a file stored on the disk. The last thing that you'll see is display this data interactively, right? For people to interact on a web page. So that's where Leaflet comes in, or display it dynamically. Again, that distinction between what is interactive and what is dynamic. Dynamic is something I specify as something that changes in response to a user input, like, okay, now you're showing me data for March, show me data for April, right? I go there and click a button, so now that whole thing is changed and now it shows you data for April, but it's still static to a point. Whereas with Leaflet, it is actually interactive. You can interact with that. You can click on it, get more information by hovering on it. That's the distinction I make between dynamic and static, interactive. So if you are storing static images, if you are working with base R plotting, we'll see what base R plotting is. We'll see what ggplot plotting is. But just to remember, if you're working with base R plotting, you have to create the output format first. So as I'm saying save this as a PNG, this is the file name, that's the width and height that it needs to have, that's specified in pixels. Then you call your plot function, and then you say dev off means stop printing now, close the file, and then you have a PNG file. If you are working with ggplot, then you build that plot first off. You don't really need to specify any device or anything. Just call ggsave as it's highlighted, tell that that's the PNG name, and the device is again PNG. I'll talk what devices are in future in a little bit. So basically, devices are your ways of outputting data to a certain file format, right? You have various devices for PNGs, for PDFs, for JPEGs, for SVGs, for TIFFs. Depending on which device you use, the data will be stored in that format. So again, like base R plotting is a little cumbersome because you have to first open a device, do all your plotting, close that device. If you forget to close that device and do some more plotting, those plots are gonna either they're gonna get added to that old plot or they're gonna replace that old plot. So if you forget that dev off, your plots can go wrong. Whereas with ggplot, it's simple. You build all your plots what you want and then just save that plot with ggsave. There's another package called Cairo, which claims to give you high quality graphics devices for a lot of these packages. I've used it. I haven't really found it any better than the ones that I've already listed at the top, but maybe under certain situations or circumstances, Cairo is a better choice for devices. So you'll just see like Cairo PDF, Cairo SVG, Cairo PNG, just like exactly the same thing, but with a Cairo prefix. Maybe something to look into. So this is raster data and vector data plotted side by side. How many of you can see the quality difference? The vector data is much better, right? Like if you can see. And if for those who are not convinced, let's do this. See, as I zoom in, the edges, they start to get jetted, like it just starts to get blurry. While as with vector data, it's smooth because it's a vector representation. So no matter, I could blow this up to 500 times and it's still gonna be smooth. And this one is just, it starts to get blurry at this thing, right? Now, if you are into, like if you are a technical person like me, the next logical question should be, what are the sizes of these two formats? Like, okay, the SVG is really nice, it's big, what is the size? I can tell you that raster data is 26 KB. Just that raster image, that the one that you see over there is just 26 KB. Any guesses as to what the SVG is over there? It's 1.4 megabytes. So 2 orders of magnitude more than that. For that much amount of difference, you better get good quality, right? Like, so it's something that you need to be aware of when you're making choices. If you are really putting it in a web page that is going to be accessed by 1 million users, saving off even a few kilobytes will do magics to your bandwidth bill, right? But if it's something that just needs to be accessed for a certain amount of people, choose SVG because it's going to give you a much better format. I've simplified that a little bit, like you can optimize that image over there. I've just used base plotting. There are options in which I can optimize that. And similarly, there are options in which I can reduce the size of that SVG as well. I haven't talked in detail about that, but typically, if you have complex polygons, as you have over here, your vector representation, SVGs, is going to be much bigger than the raster representation. So you get quality at the expense of size. Animation is really easy to get started with. All you do is build a bunch of images that you want to show in a sequence, and then just use the GG animation save or animation.save. I tend to use the second package more than the first one, but that's just a personal preference. Both of them are really nice, and both of them allow you to save data into different formats. Some of the formats require you to have external libraries installed, like some of them will require you to have ImageMagick or FFmpeg or some of those other external libraries. But just read up on that. But it's really very, very straightforward. I'm going to show you code for how to do that. But here's just a quick animation for you. This shows basically US population from 1900 to 2010, how the population density has changed, well, how the absolute population has changed. As you can see, in 1900, the California population was not that high, and then it increased. So that's probably one of the places where you typically end up using animations, where you want to show certain temporal data over a period of time, right? So when you want to save these images into your PDFs, your HTMLs, your Word doc, you'll do that using R Markdown, right? Like you'll have your R Markdown code chunks, and in there you generate that. And this is all there is to it. You start this thing, you give certain figure options that you want, alignment, and you run the code as though you're running your normal ggplot to plot, and it gets plotted as an image. So R Markdown or Knitar is smart enough to realize that it's an image coming in, and it'll plot it as an image. I am always at a loss when it comes to R Markdown or Knitar. Like I'm always forgetting what these options are or what are the optimization techniques. So I've given you 3 links. I always have those open whenever I'm working on R Markdowns, right? So all this thing was written in R Markdown. I have the links. I had those links open in a browser window. There is an excellent blog post explaining all these details by a guy called Zev Ross. If you don't know, he's like one of the good contributors into our spatial ecosystems. He writes excellent blog posts. I used a lot of his blog posts as inspiration for these slides. And that blog post basically will tell you everything you need to know and a lot more about how to embed images using R Markdown. And one of the tips that I'll give you is enable caching. As you know, or if you don't know, R Markdown can entire support caching. So if the code doesn't change the next time you need that document, it's not going to rerun that code. It's just going to read it from the cache. Extremely handy. I don't see any reason why you should have that enabled, not enabled. Just enable caching. That would be my tip. So those were static maps. What about dynamic maps? So dynamic maps, one of the things you can do is in Shiny applications or R Markdown HTMLs, which are Shiny. How many of you know Shiny? Awesome. So I don't need to explain that. So you can use Shiny applications to display these maps dynamically. The maps are dynamic as in they change as per user input, but they are not really interactive, right? Like it's still a ggplot2 map that you can't really hover over or you can't select, deselect, what have you. So I just found an example of that on this thing. Full disclaimer, this is not mine, and it seems like it's not even showing up correctly. So yeah, there should be a map over here that is not showing up for some reason, but if you were to open it offline, you'll see that. And then lastly, we come to interactive maps. Let me see. Yeah, I'm still good. Interactive maps always make sense in a web environment. You can zoom in, you can toggle stuff, you can add more information by like looking at pop-ups or just like hovering over stuff. If you have never done interactive maps before, my advice would be to get started with Plotly, because Plotly just allows you to take a ggplot2 map and make it interactive by just one single call. So if you know how to do plots in ggplot2, just use Plotly. Another advantage of Plotly is that it is a generic plotting library. It's not specifically for maps. You can do any kind of plots with Plotly. So Plotly is like, would be my #1 recommendation for anyone who wants to get started with interactive plotting, not just mapping. Then you have Leaflet and the ecosystem, which is extremely powerful, extremely flexible, but can be overwhelming if you are really new to that stuff. Another alternative to Plotly are Arbokay and HighCharter. How many of you even know about these packages? Yeah, good. So how many of you know that they can be used for mapping? Good. So some of you. So Arbokay and HighCharter, again, like look at those as an alternatives to Plotly. You don't really need to go down the path of Leaflet if you don't want to. If you want to make simple interactive maps that you go on web pages, Plotly, HighCharter, Arbokay are more than enough for your needs. And I say that as one of the authors of Leaflet package, right? So all these above are what are called as HTML widgets. HTML widgets are basically R's way of wrapping JavaScript and a bunch of HTML together. Like you write code in R and it's a HTML widget, so out comes a HTML and JavaScript code that works on any web page. That's all there is to it. There is a package that I wrote, Widget Frame, because one of the things that I found with HTML widgets is when you start embedding them in things like presentations or things like your blogs, like do you know about Blogdown, which is Yuhui's package for writing blogs in R? If you start embedding HTML packages into that, because of certain CSS and JavaScript limitations, they don't tend up to show correctly. And Widget Frame allows you to isolate widgets so that it will display correctly. I'll show you some of the widgets later on in part 2 of the tutorial, and they are all embedded with widget frames. So it allows me to isolate widgets correctly. And HTML widgets now have the ability to talk with each other. Earlier, they used to be isolated instances, so you could have like a graph and a bar chart which have no way of interacting with each other. Crosstalk allows you now to have bidirectional communication between these widgets. So you can select stuff in one chart and it will automatically update on another chart, or you can select stuff in a map and it will automatically allow the corresponding, say, bar chart visualization that is based off that. So that's what Crosstalk is. And it doesn't need Shiny. It works on web pages straight up. You don't need a backend server environment like Shiny for that. And obviously, the maximum flexibility is combine HTML widget, Crosstalk, and Shiny. I mean, that's just level 5 wizardry when it comes to visualization. If you know how to do all of that, I would love to learn more about that from you. So that's it. That's part 1 of the tutorial. And I know it was a little boring. It was a little heavy. But the good stuff is coming up. And this is now just plotting, and you're going to see a lot of options and a lot of hopefully good plots that will probably just blow your mind away. So stay tuned. Don't go for, like, what do they say? Like, don't go anywhere. Just come back to the same session or whatever. Part 5 will be static maps, and part 7 will be dynamic maps. Lots and lots of plots, lots and lots of options. If you are in Docker or if you have downloaded the GitHub repository, on the repository there is a folder called INST. Inside INST there are 2 folders, presentations and notebooks. Presentations has code for all these slides, and notebook has basically all these slides, the plots that are present in all these slides in a notebook format so that you can interactively run them on your own, make changes, play with it, whatever you want to do. So yeah, we will, oh, this is 11:1, that's awesome. That's like exactly on the dot. We will meet over here at 11:30 after a coffee break or something. So in the meantime, I'm here, so just if you have more questions, feel free.